Assalamualaikum and hi. My name is Muhammad Eirshady bin Izzuddin. Today, I will present my computer-aided engineering project. The title of my project is The Effect of Different Width and Length of a Vacuum Cleaner Nozzle Head on Airflow Velocity and Pressure Values. This project explores the performance of vacuum cleaner nozzles by analyzing how changes in nozzle dimensions, specifically width and length, affect airflow velocity and pressure using SimFlow software. This research is crucial for optimizing design to improve the efficiency of vacuum cleaners. Let me start with the purpose of this study. The primary goal of this project is to analyze the performance of vacuum cleaner nozzles. I focusing on how the width and length of the nozzle head affect two critical factors: airflow velocity and pressure. By examining these two parameters, I aim to determine optimal nozzle dimensions that can enhance cleaning performance. Using computational fluid dynamics simulations in SimFlow software, I conducted detailed analysis of airflow dynamics and various nozzle designs. This brings us to the project objective, which as follows. Number one, analyze the impact of varying nozzle width and length on air velocity. Number two, identify the relationship between nozzle dimensions and airflow velocity at the outlet. Number three, determine the effect of nozzle dimensions on pressure. To achieve this objective, the project followed a systematic methodology divided into three main stages. Stage 1, geometry creation and setup. The nozzles and their fluid domains were designed using CAD software. These designs were then imported into SimFlow software, where boundary conditions were defined, including the inlet and outlet parameters for the airflow. Stage 2, mesh, mesh optimization and simulation parameters. A mesh convergence study was conducted to refine the grid and ensure a balance between computational efficiency and result efficiency. The simulation was set up using steady-state, incompressible flow conditions with air properties. The simple solver and runs turbulence modeling were applied to replicate realistic airflow behavior. Stage 3, data collection and analysis. Velocity and pressure data were collected across various cross-sections of the nozzle. The effects of different nozzle width and length of on airflow dynamics were analyzed to determine the optimal design. The study involved both dependent and independent variables. Dependent variables, these are the factors we measure, specifically the velocity of air and pressure of air. Independent variables, these are the factors we control, namely the width and length of the nozzle. By systematically varying the independent variables, we could observe their direct effect on the dependent variables. Mesh analysis. Mesh analysis played a crucial role in ensuring the accuracy of our simulations. The purpose of this step was twofold. Number one, to achieve a balance between computational efficiency and result precision. Number two, to minimize numerical errors and ensure stable results. A mesh convergence study was performed. Multiple configurations were tested by progressively refining the grid. The optimal mesh size was determined to be 24, 90, 50, with a minimal percentage deviation in result of just 4.05%. This mesh configuration reduced numerical errors while maintaining efficiency. Further refinement beyond this point showed negligible improvements, confirming that this was the ideal choice. Color contour plots. The result of the simulations using color contour plots. These plots show the airflow velocity and pressure for different nozzles. For example, nozzle with 1.4 cm width and 12.5 cm length, the velocity was highly concentrated near the exit with uneven airflow distribution. Pressure dropped steeply near the nozzle outlet. Nozzle with 2.4 cm width and 12.5 cm length, this design exhibited more balanced airflow distribution, with smoother pressure gradients and improved stability. Similar patterns were observed for wider and longer nozzles. These visual representations provide a clear insight into the performance of each nozzle design. Analysis. Now let's discuss the key findings from the analysis. From the analysis, narrower nozzles, these produce lower velocity and pressure values. For instance, a narrow nozzle achieves a velocity of 1 to 6.7 meter per second and a pressure of 3,537.8 Pascal. Wider nozzles, this allowed for greater airflow, achieving higher velocity and pressure. The widest nozzle achieved 294.83 meter per second velocity and 35,326 Pascal pressure. Longer nozzles, this stabilized the airflow, leading to more uniform velocity and pressure distributions. They also reduced turbulence and energy losses, contributing to better overall performance. From the results, we observed the following trends. Number one, for velocity contour analysis. Narrow nozzles produce high velocity near the exit but had uneven distribution. Wide nozzles exhibited even velocity distribution but lower peak velocities. Long nozzles stabilize airflow, ensuring uniform velocity along the length. For number two, pressure contour analysis. Pressure contour analysis. Narrow nozzles show a steep pressure drop near the exit. For wide nozzles, achieve smoother pressure gradients with better distribution. And for long nozzles, improve pressure stability and reduce turbulence. These findings highlight that increasing nozzle width significantly enhance the pressure, while longer nozzles stabilize airflow and improve overall performance. The largest nozzle, with dimension of 3.4 cm and 12.5 cm length, achieved the best results, offering a balance between velocity and pressure. To conclude, the study successfully analyzed the effects of varying nozzle dimensions on airflow velocity and pressure using CFD simulation in SimFlow software. Mesh convergence was achieved with a 24-90-50 configuration, ensuring reliable and efficient results. The findings the findings showed that narrow nozzles produce higher velocity due to restricted cross-sectional areas, aligning with the continuity equation. Wider nozzles allow greater airflow and higher pressure, while longer nozzles stabilize airflow and reduce energy losses. The largest nozzle, with dimensions of 3.4 cm and 12.5 cm, delivered the best performance by achieving balanced velocity and pressure gains. Thank you so much.